All righty. We have a good clap. That was a good one. You can tell because it reverberated. But yes, on today's agenda, like the clickbait said, we're going to derive the fine structure constant. What is the fine structure constant? All right. So, as folks are rolling in to join us wherever on the internet, from whence you happen to originate, we're going to erase the board. We're going to fill up this time as folks that are joining us now and temporally in the future can feel free to skip ahead. But today we're going to be talking about alpha, the fine structure constant. It's the strength of the electromagnetic coupling. At least that's what Professor Wolfram said one of the last times. It's supposed to be one of the greatest dang mysteries in physics, along the lines were said by Professor Feynman. Yes, even though he may have created QED, we needed to derive this from measurement in order to figure out what the heck is going on and actually plug it into the equations to get stuff to work. So that's a little bit of a recap for basically the whole point of this. All right. So the fine structure constant, as we can see in the little thumbnail, it's that generally that 1 over 137. Why? Because it seems like such a random thing. 1 over 137. Well, to be fair, 1 over 137.035999, but who's counting? Uh, but that's the level in which we have confidence. Once we get to around that 10th digit or so, our confidence seems to wane, or at least depending on the experiment, because the experiment from, I believe it was Berkeley Labs in like 2018, they had it to be like 137.035999 zero, I believe, something like that. More recent experiments have it, I think, like one something there. And remember, it's a reciprocal, so if you're turning it upside down, the numbers will go in the different directions. Okay. So alpha, here we go. Let's do this. Let's go into a little bit of history here, shall we? Oh, we shall. All right. So we got alpha. Yes, I'm literally just writing alpha on the board. As long as my brain can compute it, should be able to spell alpha. I spent enough time on Wolfram alpha. And alpha is this little a little kind of fishy A right there. Yes, it looks like a Jesus fish. Um, listen, hey, whatever denomination you believe or don't believe in, that's up to you. But it looks like a fish. Okay, so we got alpha, and that is equal to. So we'll do this. Do alpha, a little fish right there, is equal to. This is the official definition, according, well, at least according to Wolfram Alpha and basically the fine folks on the internet. You have elementary charge squared. I know there's going to be a review for a number of folks. That's all divided by 4 pi h bar c, the speed of light, and E naught, the the electric permittivity of free space. That is equal to alpha. Okay. Again, some folks, maybe you look into it, like, all right, we got elementary charge squared, it's over 4 pi. There's like some spherical type thing going on here. And we got h bar, and it's taking some elementary unit of action. Well, at the speed of light via the permittivity of free space. Well, actually, that's probably a pretty good definition. Now, what does that actually mean? It's like, oh, that seems like a lot of stuff going on. It's like, there's one thing I've learned from Professor Wolfram. Sometimes boiling things down into their simplest parts may help us better parse what might be going on, what might be going on here. So this gives us a dimensionless number. Okay. Since it's dimensionless, that means that all this stuff that has dimensions in there are ingredients of reality. And let's just go over our stuff. So our stuff, aka the ingredients, and ingredients. Oh my God. I can't spell. There we go. Ingredients. I think that's spelled right. Ingredients. These are dimensions. Dimensions of measure. Dimensions of measure. Cool. This is the stuff where our instruments go click. They measure a magnitude. It gives us something. We believe we are actually measuring something that exists. Some folks would disagree with that. Maybe we're just constantly collapsing into all this, and then there's all these branches all over there. Some folks believe that. Some folks don't. It's kind of like almond joy. Almond joy's got nuts. Mounds don't. Not meant to be a derisive statement. It just came off that way. All right. So our dimensions of measure. We got. What do we got? We got time. We got space. You got charge, and you got mass, and we got temperature. All right. And these are, of course, related to base building blocks of reality, we would claim, which would be the Planck unit. It's the Planck units of this. Oh, let's uh small t sub p Planck time space. Oh, that's the basic one-dimensional form of that is length. You got a length, you got a ruler or something like that. You just go from a point to another point, you got a line. That's a length. So we do L sub p, Planck length. Charge, well, we represent charge with Q. Why? Because that's what we do. So it's Q sub p. Mass is Planck sub mass. It's Planck mass, excuse me. It's M sub p. And temperature, it's big T. Why? Because it's 10 to the 32 degrees Kelvin, approximately. Big T sub p. Planck time is actually 10 to about the minus 44. So it's really small. Hence, we use small t sub p. AKA, why am I off by 76 orders of magnitude? Because I used the wrong stuff. See, if you're gonna do baking or dimensional analysis, you want to make sure you have the correct ingredients. Otherwise, it's probably not going to taste too good. Um, okay, we got this dimensional stuff, and then you start looking at it like, well, like charge. That's charge squared. All right, so I got two things of charge. All right, 4 pi. All right, that's a geometric circular type thing. Hey, Rick, good to see you, my friend. All right, and we got h bar. So you know, action. What's that? That's a mass, an area, because it's two dimensions of length, and then it's per tick of time, because it's divided by time. So we get a time dimension in there. Okay. And we got c, which is the speed of light. It's like, all right, well, hey, let's just write this out because we got a board here. All right. So we've got charge 2. All right. So we got Q2. We got two things to charge. All right. So we got geometric action here. Okay. I'm not actually going to do this all up because I'm realizing I'm going to have to do the square roots and stuff like that and go to the Planck charge. So I'm just going to confuse myself more. We'll finish up there. Speed. It's length divided by time. So we got a unit of length divided by time and the electric constant, which I actually don't remember off the top of my head. Okay, so it has to have a unit of mass because that's mass area. So let's get mass in the denominator. Long story short, this all cancels out. So it ends up being, you can reduce that whole jazz to this elementary charge over the Planck charge, Q sub P, and then we square the whole dang thing. And that is equal to that, my friends. I don't know, that seems pretty computationally reducible to me. So what does this mean? All right, our elementary unit of charge is divided by our boundary of charge itself, and we square it. And then we get alpha. Okay. For those of you not paying it that or maybe new to this, if we just do this, we're going to go elementary charge over Planck charge. We just do this guy. Well, that's going to be we'll move it over because it's not actually equal to that. It should be actually precise in what we're saying, even though I'm just saying it out loud and figuring it out right there. But all right, so if we just have elementary charge over the Planck charge, we get, we're going to call J1. Yes, that Cyrillic symbol there. And we get a 1. Why? Because that's going to be the numerical part of the answer. Hey, Keishel. Thank you for joining, my friend. Yes, we're just going over the mystery of here. Let's get more clickbaity. 1 over 1, 3, 7. Question mark. Okay, see, if we had a question mark, we're asking a question. We're not making a declarative statement. So we're okay in some universe, I guess. Best to be as precise as we can. And when using hyperbole, make sure it's apparent. It's my opinion. All right, so where were we? All right. So we're going to this, and then you notice this, and again, people have noticed that and everything. It was John, oh God, his name sounds kind of like McCracken, but it's not actually McCracken. McCracken did the intro to Breaking the Multiverse. Let's all wish Fizz a speedy recovery because she has like VTuber flu or something. That's why we don't have that show today. So swift recoveries to Fizz and Piper. All right. Who are totally two separate entities. Okay, we're talking about dimensions. We can go into the fourth dimension or so a little bit. So it's breaking a wall. Okay, some dimension of society that I still haven't really comprehended. Okay. So where should we go from here? The whole point, how to derive it. Okay. So when you see simple things like this, it's like, all right, maybe we can reduce this. And again, all these things here, it's like, well, you got to get this from measurement. You got to get this from measurement. We got that from measurement because we're measuring the two-way speed. And the measurement on this it's very close to something in those last couple of digits, sir. Might depend on the experiment, might be throwing us off. I believe I might just be making that up. Trust, verify, verify. Those are two very good things to keep in mind. Okay, since we got that there. All right, we're going to go into other ways to do this. Let's share with the class. We'll go over Weiler's constant because I saw some folks talking about it the other day. It was the alternative propulsion conference or something. Hey, Dave. Good to see you, my friend. Yes, yes. We all wish them swift recoveries. Yeah. Go humanity and celestial wolf girls. All right. So let me just bring up another thingy over here. And then let's do this. All right. So we're gonna go for a number, a particular arrangement of digits in a particular way. No, we don't need the Planck time right now. That's not what we're talking about. We're talking about was it Weiler's constant. See, it comes right up. It comes right up on Wolfram Alpha. That's website is free. You just need to go to wolframalpha.com. Or you can go. Am I even logged into premium? I think so. I don't even know. Who cares? Oh, oh wow. That was right. It does seem a little laggy today. Either that or I'm just jumping around too much. Let's refresh our request. Oh wow. It is laggy, or at least maybe the database is being taxed. All right, well, we don't necessarily need Wolfram Alpha, at least for this point. Wireless constant. All right. What is this thingy here? Wireless constant is defined as the alpha Weiler, I believe, is 9 divided by 8 pi squared, multiplying by pi raised to the fifth divided by 2 raised to the fourth times 5 factorial and the 1/4 over there. And that gives us 1 over 137.0360. And now one of the reasons why this works so well for so long is because after this 3 here, it actually goes 5, 9, 9, 9. So the six actually fit pretty well until we got past that and we got higher precision in our measurements. Oh, aka looking for group muon collider. Apparently, there was just a meeting wrapping up, and they're talking more. Yes, yes. As I'm wriggling my hands together, awaiting the great new muon collider for totally my own selfish purposes, to either falsify or verify that prediction on the Higgs. Yes, it's okay. It's okay. It's for science. We can justify it then, right? But okay, okay. So this thing basically is used. It basically gets the about the first, 5 digits of the fine structure constant there. It's so good that it lags out. It's lagging out Wolfram right now. It's so good. It's yeah, definitely laggy. It's not just you. I think no. I think they're getting ready to do another update or something. So this usually happens. But yeah, wireless constant is there. So let's try some other things. Let's just see if normal stuff works. Gonna do 1 plus 1. Oh, oh, I think. Oh no, no, no! It's the entire system is lagging right there. Okay, well that's fine. Well, we'll access from another avenue. Why? Because so we can actually make a notebook for this. Let's do our let's play notebook. It might be. Let me check real quick because sometimes it's coming at it from a different access point. So maybe this is what's lagging it. Let's just try a normal Wolfram thing. I assume it would probably be laggy too, but let's see. Enable dynamics. There we go. Let me show a class. So we can go through and let's do this. Yes, let's play. Oh, it actually just did it. I have no idea if that's because it just started working. Did it unlag? Let's see. Um, no, I think yeah, yeah, this end is actually working better. It's still not processing on that, but it can do 1 plus 1 at least in the notebook. And I did. Hold on, let's see if we can get the full Wolfram Alpha results. Oh, no, it is actually working. Okay, so it looks like it's prioritizing whatever is accessing the hits right there. Okay. So, oh, typical human computation. Oh, this, I, I mean, I have, it's giving me all this extra relations to human statistics and stuff I didn't even know. Okay, so, all right. So we'll close that off. All right, so delete that, boom. All right, so let's do it this way. We'll go back to our friend over here. So, Weiler's constant. Let's see. There we go. It's giving us the stuff right there. All right, it has that jazz. Okay. So that gets 5 significant digits of alpha, which you can even bring up right here. So we'll do structure. No, not emojis. Constant. Okay. You get alpha. Yes, it did the thingy that I wrote on the board there. Okay, it did the rest of the thingies that I wrote on the board there. Okay, that's fantastic. All right. But we're just gonna we'll output this number right here. There we go. Quick formatted pod. We can delete this and make it a little prettier. Boom. Okay. Fantastic. All right, we got that thingy right there. All right, let's just engage the code that just happens to be there. Okay. So now we got a good number of digits. Actually, let's bump out Weiler's constant too. Well, Weiler's constant. Well, full Wolfram Alpha results. We'll pop out the pod. Pop out some pod context. Boom. Okay. We'll delete the rest over here. There we go. And I don't. Okay, I deleted the other thing. All right, let's just jump into it. So, are there other ways that we can format this? Dad, would you like to take over? This is kind of your thing, so okay. So, oh, okay. Well, it's all right. So there are other ways. So apparently, rumor has it, se- several years, number of years ago now, that somebody had brought something to Thad's attention on math, one of the math stack exchanges or physics stacks exchanges, where it's like you had a certain combination. You could do something like 1 over x plus x plus x cubed over 2 pi. Set that equal to, you can do I raised to the I raised to the j. Well, we'll just do I raised to the I right now for simplicity's sakes, because this is what was originally there. Raised to negative pi over 2. So negative pi over 2. All right. And basically, long story short, you get more digits than Euler's constant there. You probably get about six or seven-ish for this guy right here. And it's like, oh, that's kind of cool. So if this we get like, I think it's like 4 digits, and then we got Euler's constant. We get like 5. Let's say this in this form, we get like 6. It's like, okay, so this is well within pop culture right here, 1 over 137. This, so people know about it because it happens to be a closer approximation. It gets 5 digits. This apparently got almost no attention and it gets like 6 digits. So it's like, all right, not a lot of people know about it. And then one of the greatest things that I learned from Thad is he told me, he's like, well, this seems to be an actual type of thing that maybe somebody could parse. It's like, this seems like a pretty simple expression. Seems to have a lot of great geometric properties that we'll get into in just a minute. It's like, what if I assumed it was right? This is probably around the time where one of the best estimates was the Berkeley labs, and they had measured it, and you put it in, and you look for the digits and everything, and it's like, well, what would you need to do in order for this expression to be correct? Well, you would need a lambda. You would need to subtract something out. What you need to subtract out happens to be the magnitude of the Planck mass. So you can, magnitude, so straight bar, or you could just write it as MP over kilograms, just to take the dimensions out. Which maybe that's even that in and of itself is telling us something there. So you plug this in, and then you happen to get the fine structure constant to the all known numbers. To be fair, right now, the all agreed upon digits, I think it's like about 9 digits right now. And then from there, because Codat has an update, and then they've updated it to something different. Because before, the last digit was, let's see, it was, goes 999, and then I'm trying to think about how you write it. But long story short is it goes to, rather than, let me actually look it up. Let me get it right here. Rather than me trying to like fight in my brain, because I'm remembering it in its normal form and its inverse. Hold on. Sure, constant. Full results. Okay. So this number right here, yeah. So when you do it out, you get 5, 6 right now. It used to be 7. Now that doesn't sound, because we're talking about which 1, 2, 3, 4, 5, 6, 7, 8, 9, like 10. I count that right. 3, 4, 5, 6, 7, 8, 9, 10. Oh, they usually do like the number 3. All right. So at least in this form, it's like the 11th significant digit. Okay. Doesn't sound like much. However, the error bars they had before at one point was pretty large. It was like 50 or 60 for like the last 2 digits, because there was some uncertainty. Now, there was a recent experiment, I think in like 2023, where they were measuring, I think it's G minus 2 of the electron. And basically, they had constrained the fine structure constant to lower error bars. But even within that experiment, they brought up, it's like, well, at the time, there was about a 5.5 sigma tension with the fine structure constant at that time. And they're like, well, we seem to be getting different results depending upon the type of experiment. Might there be a clue in there? I'm very biased. I think there might be a clue. Maybe the other experiments were just wrong. Maybe our current technology is better. Okay. Because right now, full disclosure, at least this expression right here, with how they have it mapped out right now, because now they give a few extra significant digits to what they had on the experiment. Um, it goes down to right now, I think we have about a 7.5 sigma tension with the current error bars because they cut the error bars down by like a quarter from the experiment, where they even said when they cut off what we knew, they ended up the last nine. That 137.35999. They lopped it off there because, like, listen, this is where we have agreement for like the past about 20 years or so. And then we have your deviation. Okay. So maybe there's something that we could learn from this. Maybe this is the reason. Maybe this is just off. Maybe everything is completely wrong. Maybe the new measurements are precise. Okay. Well, if the new measurements are precise, we would need to modify this. What we need to do to modify this? You divide the magnitude of the Planck mass by root 2, and then it's smack dab in the measurements. Literally, it's eerily in the center there. So that makes me a little skeptical. But if we're going to go by the measurements to what we need to get out for a dimensionless number, this is what we would do. And we are literally smack dab in the center of the measurements. So, well, let me readjust the audio because I think I set it to the other. Okay, yeah, go ahead. Yeah. Hmm. Hmm. Oh, right, right, right. Mhm. Yeah. Okay. Well, it's right. So that is bringing up the point where, um, unless you're a very obsessive person spending an enormous amount of time looking at these things, paying attention to the updates through hundreds and hundreds of different measurements and recommended values, you might not notice that from one update to the other. For instance, the electron in this most recent update had about a 4.5 sigma swing. The proton had about a little over a 4 sigma swing. Now, again, these are measurements that we have to like 12 significant digits. We got like 10 significant digits, like straight on. Those last two digits, they've been swinging back and forth a bit there, and I think even maybe the 10th digit for maybe the proton. But what else we got? Okay, yeah. Oh yeah, yeah. No, no. Thad was no. I had the other audio on. Thad was just bringing up that if we did adjust this by root 2, this right here, I should actually go into more detail. This, when you set up this equation, we're calling this the hyperbolic partition equation for right now. Basically, we get four answers. We get four answers. Okay, and those answers are like we did right over there. Just label you label them as X or whatever. We just label it as Juz for accounting's sake. And we get J1, J2, J3, and J4. Okay. And then we have the geometric forms, but basically these are the four roots of the equation. Whereas if you plug in any one of these into these x's, that statement will hold true. So basically, he was saying that if we did a root 2 there, that would adjust J1, thereby adjusting all of these. Now, you could say, oh, well, maybe that's a bad thing. Maybe we'll get things more precise because, I mean, again, the Planck mass basically does have an offset of 8 significant digits. So any of the changes end up coming at some point after the 8th significant digit there. Um, approximately maybe the seventh of some of them, because root 2 divided is about 0.69 or 0.70, something like that. But the other interesting thing is these things have magical properties. Well, he's saying magical. What does he mean? Well, if you happen to do certain things like, I don't know, you do Je1 plus Je2 plus Je3 plus Je4, you get 0. It's like, wait a second. These guys sum to 0? That seems rather odd or very useful there. It's like, all right, you sum all these things together, you get 0. Okay, and that's like, all right, well, maybe what if you do something like this? You do that same thing. 1, but you go to 2. They're gonna multiply. Just 3. Just 4. What do we get? We get 2 pi. Wait, we get a circle? WTF, mate? What the heck is going on here? And then we get very fancy. We get very fancy. Well, we'll sum the squares. We'll do Je1 squared plus Je2 squared plus Je3 squared plus, yes, again, we're being very repetitive. Je4 squared. What do we get? Negative 4 pi. Wait a second, that seems to be an inverted sphere. It's not like anyone has been insinuating that before. The inversion of a torus is a hypersphere or something. I mean that might actually help us make sense of it, but if only with someone we're talking about that or thinking about these things. I'm sure there are. Okay, looking some more activity. Hey, Jax. Is there no comment on infinity? It's it's hard to say. Let's see. Enjoy this is cycling. Okay. Rick is commenting. Okay, so what we should do is this should be I raised to the J. Because John Williamson, God rest his soul. Let me make this a better J. They. So I raised to the J. Why? Mathematically on Wolfram alpha, they're both representing the square root of -1. But we want to be specific because we're talking about orthogonal planes. We're talking about things that are lining up. So we can go from, all right, orientation, 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 orientation. Okay. So, and even Casey had brought this up before, where if you see an infinite tower power of I, again, we're taking the numerical factors in order to compute and find things. Is that a good description of what's actually going on? No, we're talking about there's going to be some form of an orthogonal rotation. We believe, I happen to believe there's probably a limit to that at some point. It might be a ginormous limit, it might be a minuscule limit, but there's going to be some form of a limit. Now, what might be unlimited, Jax, to address your point, is the one place where I think infinity may be something we could talk about would probably be time, because time is probably, it appears to be, if we were to view this as some form of turtles, our primordial turtle there, maybe it's turtles all the way down. Maybe it's literally turtles in time. That was a fantastic arcade game. God, I love that. But hyperbole aside, this also happens to be the largest magnitude. It is the smallest part that we have, but within a system utilizing the dimensions of measure, our ingredients of reality, time, space, charge, mass, and temperature. Time appears to be the most fundamental right there, or at least in a magnitude. And that's under what we're believing right now. So we've got dimensional ingredients. We've got the fine structure constant defined in these terms. Now, the beautiful part about this term is you get elementary charge participating the Planck charge squared. I don't know. That sounds like some orthogonal alignment between our basic unit of charge and the boundary of charge itself. Okay, so we were talking a little bit about this form. So we have this form. What is this? All right, we got some stuff. We got x. Okay, we got 1 over some stuff. We got plus some stuff, plus a cubic volumetric stuff. It's doing a circle thing. We got like a full circle there. And that's set equal to the imaginary number. So the square root of -1, we're viewing that as an orthogonal plane, set to another orthogonal plane, and we're raising that whole thing to negative pi divide by 2. So we've got like a small twist going the other way, and we're subtracting out what we believe to be the Planck mass gap. And we have good reason from poster that's filling out very well, and we just need to subtract out the magnitude of the Planck mass gap there. Okay, maybe it's root 2, maybe we need to multiply it by log 2, something like that. But this seems to get the digits very well to all the known digits, and it seems to provide, let's say, the method of decomposing the constants of nature. So that's basically how I view it right there. And it's like, okay, it happens to get the number. Why? Because, well, basically, if we just do this, le 1, we square it, we get alpha. Okay. Because elementary charge divided by Planck charge equals J1. If we square it, we get alpha because J1 is basically the amplitude of the fine structure constant. I believe I'm saying that right, or maybe the fine structure constant is the amplitude of the other there. I believe J1 is the amplitude. Let's see, where else we got? Da, da, da. Let's see. Well, in order to get from this to humans, I'm gonna digress back to my turtle of time. Given enough time, a lot of fantastical stuff can happen. Now, has all this fantastical stuff happened before? I don't know. I wasn't there, or at least I don't remember it. Not saying it didn't happen, because if you're dealing with eternity, that is a long time. So let's see. Oh yeah, I should probably actually do this for the class. It's actually, seeing as we actually have this thing right here. So let's just so you can verify that I'm not just a crazy person rambling on the internet, but maybe a crazy person rambling on the internet that maybe has noticed some interesting things. Okay, so let's just do our little thingy. Yeah, let's go up here. So let's do 1 over x plus x plus x cubed divided by 2 pi, so equal to I raised to the I, because otherwise I'm going to set parameters on j unless they've updated it. And I'll raise that to negative pi divided by 2. Okay, let's take a look at this guy right here. So, okay, so we'll get this. We'll go to our full things. So now we haven't subtract out the magnitude of the Planck mass gap right there, but just a note, grab a few more digits. Click on the thing. Or maybe it only has so much information. Or maybe it's just lagging. All right, I'll just take that. Take those digits. Plug it in here. Oh, see, look, it gave the extra digits. Boom. Square that thing. We broke the notebook. Try it again. Oh, making up digits. Hold on. Let's just its head. Let's go to the let's have the thingy on the end. Okay. Ooh, does it not? Oh wow. Oh, now it worked. All right, when in doubt, just hit enter enough times. With that touch, oh, that actually seems to get. Where are we at? Let's just. We get 007 007 297 297 35. Okay, and that's the digits we have, so we need at least some more digits. Let's delete those guys right there. Go back up to our thingy here. Let's subtract out. I'll do this. See if it works in this version. Blank mass divide by kg, kilograms. Oh, oh, looks like it actually worked very well. All right. Great. Good job, Team Wolfram. It's great when things actually work. Okay. Now let's make sure things actually worked. Trust but verify. That's one of the things I've learned over the years. Okay, so go back down to our fine structure constant thingy over here. We got that. We can delete these guys. Okay. Let's just put this thingy in here. Take off a bunch of those digits. Let's square that thingy. Okay. So let's embiggen this a little bit. So we can, okay, maybe that was that was a little too embiggened. Okay, we want to be on the screen at the same time. Okay. Okay, so our answer over here, we got is 0.007, 0.007, 297, 297, 352, 352, 5756. And that's where our deviation begins on the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So in about the 10th significant digit, after the zero there, and I'm sure this has nothing to do with it, but just for the record, um, we seem to have defined H bar at 10 significant digits. We did used to have 12, but our measurements kind of started to get a little wonky before there or after there. So, like the 11th and 12th digit, there was a lot of uncertainty. Yeah. Oh, really? Oh, so Thad was commenting that it seems like the majority of constants of nature on data that they have defined as a particular thing is at 10 significant digits. Sure, there's absolutely no coincidence with that. But okay, so we got that stuff. We got that little thingy right there. Um, Let me see. Uh, it's okay. Hey, Jax, I don't know what I'm talking about a lot of the time. It's okay. It's okay. I think to say that you know what you're talking about, it's making a lot of assumptions. I know that I don't know. Knowing that apparently is a very useful thing because if you know that you don't know something, then you can attempt to be less wrong. Isn't that the quest of science? Is to be less wrong, less incorrect. But let's see. Well, it's to be fair, I'm working for the Physics Monastery right now. It ain't. Hey, we are basically surviving. Anybody that wants to support us, feel free in the link below. But this is basically just an organizational run thing. Would love to get some grants and everything, and hopefully that would be coming. Or any folks that happen to have a bunch of money, or even just sharing stuff around. That's the thing. Just getting the stuff out there because it's like I don't have the answer, but it's like I'm sure there are very smart folks out there, and especially a lot of young folks and a lot of folks that are kind of getting into this. You never know what you might notice, and maybe it's been noticed before. And apparently, there's a trend along some of the most brilliant mathematicians in history, where it's like you find something in like a notebook. It's like, oh my god, this person actually figured it out, and they're like, well, that was trivial. Why would I publish something like that? And it was so obvious to them, but it never made it into the literature for like 50 years. So it's like if we have something that's interesting, maybe we should share it with the world, because if we share it with the world, maybe we can do better and cooler things and get folks excited, especially when you get folks, especially now with the internet, you can be contributing from freaking like anywhere in the world. Heck, you could be up in space. I know some folks may disagree that we've been to space. I respectfully disagree. Okay, yes, it does depend on what you mean by we. That is very fair. That is very fair. But well, you just my thing is okay. If you've got something, okay, and we'll put a box around this. Why? I think it's worth putting a box around. Because again, I am not a professional physicist by traditional training or anything. I am literally a dude on the internet, like a lot of folks out there. I was just really interested and that got burnt out by politics and people just hating on each other. And you realize a lot of people just don't like each other. What's the solution? Let's legalize dueling. That is my solution. And then the terrifying thing happened that a few years ago, the amount of support it got, I'm like, this might actually work. So rather being a pioneer in the legalization of murder, I decided to maybe try to help out and like figure out what's going on with the reality so we don't need to go down that path. That's a personal opinion there. Feel free to disagree. But all right, so why did I put a box around this before my slight rant tangent there? All right. So I'm a gamer. One of my longest held identities is probably a gamer. I love games, video games, Dungeons and Dragons, all different types of games. So when you're playing a game and you have a character, or maybe you're playing a card game like Magic the Gathering, Yu-Gi-Oh, whatever it might be, you'll have different different arrangements, different characters, different abilities. And the different abilities of a card or a character are going to set up the framework for how it can interact. So you look at the abilities of your different units and you're going to deploy them appropriately. Okay. They look at something like this, it's like, all right, this don't have any real physics stuff in it, except for literally the magnitude of the Planck mass, which apparently Chat GPT and a lot of folks say is very important for quantum gravity, whatever that might be. Um, but what do we have over here? 1 over x, okay, plus an x, okay, plus x cubed, divide by 2 pi. So like a circle that equal to the orthogonal, twist in two planes, twisting in the other way via a negative curvature divide by 2. So we're twisting in the other way, and we're setting a particular magnitude of a gap of the Planck mass. Okay. So it's got some interesting properties in this. All right, this is kind of simple. You throw this in a graphing calculator, you'll see something like, okay, and then you get your little gap there and everything. It's like, all right, that's cool. And then when you mark out all these points, you're gonna see something like this. You're gonna see like, okay, so you can kind of connect those things there. That's not quite zero because it's Joe one. It's 0.085, yada yada. But okay, so you see it in those forms. Okay, what does it get us? All right, if you square the first answer, you get something that you're not supposed to be able to compute. That's very cool. That's very cool. It's at least a geometric method. I know there's a bunch of folks, a lot of folks that might be retired engineers that have other ways to get to it. I've seen some very interesting ways. I saw somebody proposing using like 4 tesseracts and stuff like that, and then they were coming out to like 134. I didn't listen to enough of it, but I'm just like, that's doesn't seem better. Maybe they had another way that I just wasn't aware of. I'm like, all right, so you get the fine structure constant to at least all its known digits. All right, that's cool. Uh, and you get these other answers. And then that raises the question, is there more than one fine structure constant? Apparently so, or at least according to this. Now, what's interesting is if you start playing around and you start combining some of these different terms, I barely done it, but I'm pretty sure if you do like Joe 1 plus Joe 2, uh, or one of those combinations, I found something for some lattice structure in some paper that was published, I think like maybe 10 years ago or something. So if you use different sets of these different combinations, you can get different numbers. And I have a feeling, if we do more looking around, you're probably going to find some of these things built in to other places. Now, none of that might be true. Maybe only Joe 1 is a thing that's going to show up in the literature. Well, except for that place in like the CMB that's showing very weird properties at about 3.66 degrees Kelvin, which is approximately the magnitude of Jet 2. But that's another tangential side story. But okay, let's say only Joe 1 is there. It's like, all right, cool. This expression as a whole, if you sum its answers, you get zero. If you multiply the answers, you get a circle. And then if you square and sum the answers, you get an inverted sphere. Now, if you have an expression that you could put on a t-shirt, I forgot to put on the t-shirt because it's literally there. But if you have an expression that you can literally put on a t-shirt, I hear Michio Kaku, Professor Kaku, he'll say like, there exists somewhere an equation that is so beautiful, that has the ability to explain so much that you could put it on a t-shirt. Now, I hear him talking about things called God equations and stuff. I don't know about no God equation, but I thought this was cool enough that I put it on a shirt. So thank you, Professor Kaku. Uh, but if I'm viewing this as a card in a game, would I play this card? I'm like, all right, for this amount of stuff, you can get the fine structure constant to all known digits. You have a form where you get four roots that you combine to get 0, 2 pi, negative 4 pi, and we have the other formats where you can basically get I and all these other things depending on how you arrange these things. I'm like, this seems to be a pretty useful expression. If one were to play a game and you're like, what do I play? I play the hyperbolic partition equation, or maybe we'll just call it the hyperbolic vortex equation for that because it sounds more like a wizard spell. But you look at what you get out of something like that. And again, for me, if I just want that number, this is much simpler. I'm like, all right, basic unit of charge divided by boundary of charge, square that whole thing. All right, that gives me intuition. Just like even this form right here gives me intuition. All right, so we got a basic unit of charge squared, something sphere, taking an action at the speed of light via the permittivity of free space via the electric constant. That was much more of a mouthful, but these things give us different ways of showing perspective. So we're gonna let's complete the cycle. We're gonna claim it equals this. All right. Okay, I think maybe I ranted long enough. Where are we at? We're at a little under an hour. We got a little bit more time. Let's see. It's cool. What was that? Yeah, let's see. Let me just catch up with our friends in the chat. Okay, let's see. Da-da-da. Uh, yeah, no, I think no, that's one of the reasons why we share with folks. And that's one of the beautiful things about the power of the internet is there's a tool that can bridge as it teaches other folks like I'm still getting recommended videos from like 12, 14 years ago on YouTube. I go back and I'm like, oh my God, I've never heard this talk in this particular fashion, and they're talking about something because I'm going to claim here, and again, I'm not a computer scientist or anything. That's Professor Wolfram, but I think the algorithms show you what you seek. Either that, or maybe they're just trying to maximize the time you spend on whatever platform. Irregardless, which I'm allowed to say I'm from the greater Boston area, so you could say regardless, we can use irregardless. And I think even Sean Carroll put it in his book. I made a comment he liked. It's like saying irregardless of like whatever he was saying there in one of his books. I'm just like, it warms my heart to see that. But yeah, let's see what else we got here. Yes. The only problem is I don't always pay attention to these things in live time. All right, so Rick has written down some answers. Let's see. Blah blah blah. It's Here's the thing. Humans are going to human. That's going to be a consistent thing. I think we just need to accept that. If you try to bend humanity to your will, it usually doesn't go well, especially when you're trying to do it with violence and stuff. How do you do it? Well, you need to have a good story. You need to have something that folks can get behind and everything. And that was one of the reasons I kind of got out of the politics thing, because like it made me sad, because like I actually wanted to have like good discussions, solve problems and stuff. And instead it's like the person we like destroys, all capital letters, the person that we don't like. I'm like, this is it, it just bored me. I'm like, you see the same thing, and every day the worst thing in the world, it's gonna end Western society, blah blah blah. It's almost like not like anyone would ever get politically groomed on the internet. I heard folks making a big deal about that until they no longer were able to make money off of it, apparently. I wonder what happened. Remember, kids, the only color that actually matters is green. Really want that statement to be falsified. God, God. It's all right, Rick. My brain melts on a regular and frequent basis. So that's okay. Probably due to much different circumstances. But I digress. Let's see. So where we're at, what are we talking about? All right. Um, oh, the boarding evidence. Now, we'll just wrap up with this, because full disclosure, at least according to the current CODATA recommended amounts, and again, these are amalgamations of things, the recommended amount, we have about a 7.5 sigma deviation. It's like, well, it must be wrong. Or maybe telling us something. Because as Thad had said, if most of these significant digits on CODATA that we have defined, that we're lopping off the error there, are at 10, and we happen to have basic agreement through about like the 10th digit, okay, might there be another way for us to verify? Now, the other thing, there are a couple of points where we have some different agreement with even the good folks at Team Wolfram, or at least according to what is on Wolfram Alpha, the Planck charge. We do have a difference as well, because that when Thad was originally doing the calculations, we had probably about 5 digits like the rest of them or something. Now it is listed at 10 significant digits. So, but the interesting thing is, if you take the charge listed on Wolfram Alpha for the Planck charge, and then you multiply it by the fine structure constant alpha that has that deviation there, you will get elementary charge. The interesting thing is, if you take the value that Thad derived for the Planck charge, that closed forms that we had gone over the other day, and you multiply it by J1, excuse me, you needed to do the square root of alpha to get the elementary charge. So excuse me, if you take the answer to this one and you just take J1 and then you multiply it by the Planck charge that Thad has, and we get J1 times Q sub P, and that equals elementary charge. So the numbers where we do have a difference, get us the precise, every single digit that we have, at least according to Wolfram Alpha, and I think Codata as well, or at least extremely good agreement with what it has there. I could be wrong, but I'm like, wait a sec. So the two numbers where we have slightly disagreement, we actually have coming together again to something that we know pretty dang well. So it's a very interesting thing over there. And all right, I think yeah, I mean, if you're just gonna go by the information itself, 1/130 sounds like four significant digits, and you get Weiler's constant is like five, and then you get nine. I mean, we only basically just about doubled the amount of digits, so maybe it's worth putting on Wolfram Alpha. So I'm just personal opinion there, but yeah, I think that's all about we got. I'm not gonna bloviate anymore. I'll let everybody get back to their fine Thursday night. So take care of yourselves, everyone. It's a crazy world out there, but